Thanks for the invitation. Today, I like to present our recent work, which is going to build a QCD face diagram by a holographic model. Actually, this is just the part of the face diagram for the QCD method. And this is also an ongoing work. This work is based mainly, this talk mainly based on the work with my colleagues. Professor He Song, he is now a professor in Ningbo University. And Professor Lili, now he works in the Institute of Theoretical Physics, Chinese Academy of Science. And the other two others are students. As you may know, I now work in Ningbo University. Few years ago, I moved to Ningbo University. Over there, me and my colleague set up the new institute, which is called the Institute of Fundamental Physics and Quantum Technology. This institute mainly focuses on gravity, cosmology, quantum field theory, and quantum physics and precise measurement. So all of you are welcome to visit our new institute to exchanging ideas, cooperation, and so on. Here is my outline, the outline of my talk. After a very brief introduction, I will introduce our model, then discuss the thermodynamics of the model, and construct the phase diagram through the thermodynamics. And during the first order phase transition, there is associated gravitational wave. So I will show you what kind of the property we have in this model for the first order phase transition. Then I will move to consider the magnetic fields on the phase diagram. Then it's a very brief conclusion. Let me start from the black holes in general relativity. As you know, there is a well-known theory. It's called the uniqueness theory of black hole in general relativity, which says that the most general stationary black hole in Einstein material theory is the kernel black hole, which is described by only three parameters: mass, angular moment, and charge. Of course, in the universe, the black hole has no charge. Q just vanishes. Therefore, the black hole is just the curved black hole solution, which is this is the exact solution of the vacuum Einstein equation, which is discovered by Kerr in 1963. In this solution, there are only two parameters, mass and angular moment. And the Kerr-Newman black hole solution, the matrix is described in this way. Here, rho square equal to r square plus a square cosine theta. And A is angular moment parameters. And M is the mass parameter. And Q is charge. As you can see, it's easy to say. This solution, we have the horizons. When the triangle vanishes, we have the two horizons. The plus and the minus, R plus and minus. R plus is called out horizon. Is something sometimes is also out even horizon. And R minus is something called sometimes it's called inner horizon or quasi horizon. Beyond the quasi horizon, then the predictability of the general relativity is lost. The Kerr-Newman black hole solution is the most general solution in the Einstein material theory. As you can see, when the angular momentum vanishes, this solution reduces to the rational non-strong black hole solution, which is described as charged black hole solution in the static symmetrical case. When the Q vanishes, this solution is reduced to current black hole solution, which has only two parameters, mass and angular moment. And both the A and the Q vanishes, the solution is reduced. The simplest one is just the Schwarz black hole solution, is a static spherical symmetric solution of. In all such kind of solution, let me remind you, there is one special property. The horizon of even the horizon, the topological is a sphere. In this, because this point I will come back later. So I remind you this solution. The topology of sphere is the horizon topology is a sphere. Of course, the most exciting things associated with the black hole is the thermodynamics of the black hole. As you know, in the 1970s, Hawking and Beginstein and etc., the physics discovered that the black hole is nothing, just the thermodynamic object. With the temperature, with entropy, and all such kind of quantities satisfy the thermodynamics law, like the first law, second law, third law, and so on. Here, the temperature of a black hole is determined by the surface gravity, K. And the entropy is proportional to the area of the event horizon, A. Therefore, so in some sense, why the black hole is so interesting that, in my opinion, the black hole is a window to see the quantum gravity. As you know, the quantum gravity is something like the cup in my mind, in our mind, to want to build the quantum gravity and to unify the general relativity and the quantum mechanics. Therefore, the black hole, the physics is very important because the temperature and entropy, as you can see, this is a semi-classical property of the quantum gravity. Because here H bar appears here. The reason is that this is a quantum property of black hole. And with this one, another very important point is that in the 1993, the Hofft and later Susskind in 1994 said, so why the gravity is so different from other three fundamental interactions? The reason is that the gravity has a very special property, which is called the holographic. So from the black hole thermodynamics, it's very clear. The entropy is proportional to the area of some system, not proportional to the volume. In our, for example, in local quantum field theory, if you calculate the entropy for some system, the entropy must be proportional to the volume rather than the area. This is a very special property of the gravity. So this is, in my mind, this is a very important progress for our understanding of the gravity. And to realize, as you know, everybody here, you know, the ADS-CFT correspondence, of course, is a very important example to realize the holography. ADS-CFT correspondence, which roughly speaking, it says, the quantum gravity in ADS space is due to a conformal field theory on the ADS boundaries. One very special example, as you may know, like the type 2b supergravity on ADS5 plus 5 is due to n equal to 4 super Yamir theory. Here in the left, in the dual, the left is quantum gravity. On the other side, in the right side, is the quantum field theory without any gravity. Here, through this duality, we can connect between the gravity and the quantum field theory. And the mathematical receptor is just this formula. In the ADS side, some the partition function of some of the fields, like for example, like phi, and equal to the generative function on the right-hand side for the conformal field side. such kind of the equality, okay, connect the dynamical in ADS space and the quantum field theory on the boundaries. As the Wheaton said, this is ADS CFT in some sense is really conceptual change in our thinking about the gravity. So the holographic is the big jump to our understanding the gravity. As you know, from the Newton gravity to the general relativity, this is a big jump, right? Here, another jump, in my opinion. We realize that the gravity, why it's so different from the other three fundamental interactions. This is. Then, let me talk about why we talk about ADS space. Here, I show an example. For example, in ADS space, we have the planet black hole. If we set ADS radius L equal to 1, the simple solution as shown you here. Here, the function, matrix function Fr equal to 1 minus R plus cubic over R3. R plus, of course, is just the parameter, is the horizon size. Here, I remind you, here is a transverse or even the horizon, the cross section, which describe dx and dy, is a two-dimensional Euclidean space. Here, the sphere or the topology, not the sphere, but the two-dimensional Euclidean space. And for such kind of solution, it's easy to discuss the thermodynamics of the black hole. For example, the temperature of the black hole is nothing, is a proportion to the R plus. And the energy, here the energy of the black hole, E, is a proportion to R plus cubic times the V. So V is a volume or is air, which is described by the two-dimensional elements, dx and dy. So the E is proportion to the temperature up to 3 cubic. And the entropy is this is energy. The entropy of black hole S is proportion to the horizon area times V. So it's proportion 2 square times V. So from the thermodynamics of the black hole, we can easily see that the black hole behaves like a thermal gas in 2 plus 1 dimensional. The black hole is in 4 dimensional, but on the boundary, we have the 2 plus 1 dimensional. The thermodynamics of black hole is exactly as the thermal gas in 2 plus 1 dimension. From this example, we can clearly see why in ADS space, the black hole, the property can be connected to the 1 dimension less, the quantum field cell in 1 less dimension. Actually, before the ADS CFT was proposed, actually in 1996, in that time, I was a postdoc in Institute of the Theoretical Physics. At the time, people talk about the horizon, the black hole horizon. As you know, in 1972, Stephen Hawking proved that a black hole, the event must be a sphere if some certain energy condition is satisfied. However, if in the Einstein equation motion, if you introduce some negative cosmic constant, then the horizon could be at that time we call it the black plane solution, which is exactly just the way now often called the planar black hole solution. The horizon could be Leach flat, no longer the sphere. Of course, some years later, people propose something it's called the topological black hole. In that case, sphere could be hyperbolic even. In that case, the curvature is negative. Here, curvature vanishes. In this paper, we present a black hole plane solution. Is just is in Einstein-Maxwell theory. Also, we extend the solution to include the deleting fields. In that equation, or in that paper, as you can see, in equation 8, the solution is exactly the ADS charged black hole, charged black hole in ADS space, actually. Okay, here in this talk, I like to apply ADS-CFT to QCD mat because the holographic not the only to find out the property of the gravity, and also in some sense provide some tool to connect gravity and some system without gravity. As this is, of course, over the past 2 decades, people are quite interested in that. Here, and as you know, to build a QCD phase diagram is the big challenge. Here is just the roughly description of the QCD phase. On the horizontal axis is the chemical potential, and the y-axis is the temperature. And roughly say we have the 2 phases. In the low temperature, low chemical potential, we have the hydrogen gas. And with the with the larger chemical potential and high temperature, then the hydrogen gas turn to be a quark-gluon plasma. And in the standard model, however, in the low chemical potential, and this one is not the first order phase transition, but is the crossover one, is high order phase transitions. And it is believed with the high chemical potential, there is the first order phase transition. And the problem is that to figure out the end point of the first phase transition, the line. And of course, there are many like the so-called the color superconductor and other phase, lot of phase. In this talk, I mainly focus on to figure out this is the curve to identify this point, the critical point, the end of the first order phase transition line. This is why it's so difficult to figure out this end point. The reason is that, and the low energy QCD theory is a strong coupled system. So traditional, the perturbative quantum field theory could not reliable here. And lattice QCD, on the other hand, can only give a reliable information at zero density. And it means with the chemical potential, the lattice QCD is not applicable. And of course, with finite chemical potential, there are some other ways. Here I mentioned one. For example, the lattice data can be extended to the finite chemical potential through the Taylor expansion along the zero chemical potential. But because this is the perturbative method, this is only reliable for the small chemical potential case. Of course, there are other ways, for example, some effective field theory approaches. But such a kind of the effective field theory approach give different predictions. Here I show you some example. For example, for the critical end point, in the different theory, the predictions quite diverse. So, for example, here the several ways. One is showing a Dyson equation, DSE, give you different result here. And the number journal rational model gives different results. So in the critical endpoint, the prediction are quite different. The temperature, from the low, from the 40 MeV up to the over the 120 eV, and the chemical potential from the 200 up to the 1000. So it's quite different. Then we want to see whether it's possible to apply the ADS QCD, ADS-CFT to build a QCD phase diagram. From the general, the ADS correspondence, we want to build a dual theory for the QCD model. In this way, of course, we have the two ways. One is called the top-down model from the supergravity theory and discuss the effective the QCD model like the D3, D7 model, D4, D8, D8 bar model, etc. On the other hand, a lot of people use the so-called the bottom-up model. This is in something is effective model like KKS model, Gobos model, etc. And here we take the second approach from bottom-up model. The bottom is the bottom-up. We use some of the data from the lattice data to fix the effective model, then make the prediction to compare the experiment. The idea like this one. So the model we here consider Einstein-Maxwell dilaton theory. To cover the degrees of freedom in QCD phase diagram, Quaker, because of the density, then we introduce the Maxwell fields to describe the chemical potential, and also the conformal symmetry should be broken, and we introduce the dilating potential. Otherwise, the solution is exactly ADS. Then this is a conformal field. But the QCD is not a conformal theory. So we should introduce some dilatant fields to break the conformal symmetry. And our strategy is like this. All parameters in the model are fixed using the state-of-the-art lattice QCD data, because this data only for the zero chemical potential. Then make a precise prediction for the finite chemical potential. The data is mainly comes from those papers. Equation of state in 2+1 Fab QCD model and the lat QCD and finite chemical potential. This is uses the expansion scheme to get the equation state for the finite chemical potential. We will compare this one. This is mainly to fix the model parameter. And the model is simple, only 3 elements. The curvature terms, the dilaton fields, Maxwell fields. And here we have 2 parameters. One is Z phi and the V. V is potential and Z phi is the dilaton coupled to the Maxwell fields. And later we will, to fix out these 2 functions. And the equation motion, as you know, these Maxwell fields describe the chemical potential, and the dilaton fields is to break the conformal field theory or conformal field symmetry. And from this the action, we can get equations of motion. This is a dilaton fields. This is the Maxwell fields, and this is the curvature term, Einstein equation motion. And the matrix ansatz is like this one. Here, so we consider the Ricci-Flat 3-dimensional. So which means the conformal fields or the field cell is located in a flat space. And we have 2 functions, FR and eta R. And the solution are static one. then the dilaton and the maximum fields are all only depend on the radial coverage or radial coordinate R. And then suppose there is the horizon at RH, then the temperature is easily be calculated. Just the surface gravity and the entropy density, of course, satisfies the Hawking-Bekenstein area law, which is proportional to the horizon cubic. And here we, based on previous works, a lot of the bottom-up model, we choose the two functions, V, potential V, like this one, and this Z5 like this one. And we have the C1, C2, C3, C4, and C5. Totally, we have the 5 parameters. And of course, if you expand these two functions around the phi, then Z phi equal to 1. Then the maximum is a canonical term. And the potential behavior like this one. Of course, the leading term is nothing but the negative Cosmos constant. And this term gives you the mass term. And the mass is negative here, right? Then we, besides those parameters, also, of course, we have the Newton constant and other parameters. This scalar source and the renormalized parameter B, this one comes from the boundary term. Because this bulk action is divergence, so we have add some of the boundary term to cancel the divergent term. This is the so-called the surface counterterm approach. This surface counterterm can be calculated. This curvature, extrinsic curvatures, negative Cosmos constant, and the dilaton fields, and this is max fields. Because we are in the 5-dimensional, so we have the log term here. And then the unshelled action, the bulk and the shell give you the free energy omega. V is the volume free energy. You know, once you have the free energy, then you can get all the thermodynamics quantities. And near the boundary, which means the ADS boundary, we have the expansion about the phi. This is source term, this is the vacuum expansion term. Both are constant. And the matrix FR can be extended like this way. And the free energy can be calculated this way. And from the boundary term, we can get the stress energy tensor of the boundary conformal field theory. This is easily calculated through this is the partition. This is the this is the differential with respect to the matrix, and with some calculation you can get this is the expressions, and this one is the free energy. Are all determined by some some parameters here. Then we can get the TT component give you the energy density, and the TX, TX, TY, TZ give you the pressure, and the anomaly. If this is a conformal field set, then the energy minus 3p should be vanishes. If this term does not vanish, so there is trace anomaly, right? And on the other hand, here in this system, we could have a conserved charge Q. This Q is considered does not change along the radial coordinate. This is conserved charge, and if you calculate this conserved charge, you will find at horizon the Q is nothing but the T times entropy density. And on the other hand, ADS boundary, this quantity give you ADG density plus P minus mu B and lu B. Mu B is chemical potential and lu B is charge density. So from this one, you can easily calculate this. Omega, the free energy, this is the definition, is nothing but it's minus P, which is, of course, this is a thermodynamic identity. In some sense, this is a consistent check. So it means all the thermodynamic quantities here are consistent. In some reference, they did not check this one. It made some calculation because for example, energy density depend on the different way you are getting one. So this check is actually important. Otherwise, the physical quantity are not consistent with each other. Then we to figure out these parameters. So take the lattice QCD data with the zero chemical potential to fix this the 7. Let me see how much parameter. All parameters here is fixed. Totally is 5 plus 3 parameters. With parameters is determined. This is based on the lattice QCD data with zero chemical potential. As you can see from this figure, this is the solid red line is the curve given by our holographic QCD model, and this is the data are the lattice data with the area bar. As you can see, the entropy, this blue, the green one is entropy over the temperature cubic. And this is a trace anomaly red dot. And this is the pressure, as you can perfect. It's fitting is quite well up to the temperature 400 MeV. And on the other, right hand side, this one is the heat capacity. And CS is sound speed. And the K2B is nothing but the second order baryon susceptibility. This is partial lu B over d mu B. This one is also looks fitting, looks quite well. And the data, as I mentioned, the data mainly come from this paper. Is for the 2+1 favored QCD model. Here, 2+1 means the two favor is like one favor is heavy. And the parameter is, I mentioned here, is fitting result. And in the previous page, I show you the result for the zero chemical potential. How about the small chemical potential case? And because the small chemical potential, we have the two. One is from the prediction from our model. Another is from the expansion way, Taylor expansion way to get the result. As we can see, here is the entropy, this is the pressure, and the energy density. And with the different curve, this stands for the chemical potential over T. From 0 up to 3.5. It looks quite good, right? And here, this one is a result for the lattice QCD quantitative and finite chemical potential from the alternative expansion scheme to get the result, like one. And on the other hand, here I take the compared to the previous study. Here in this paper, they are also build a model, QCD holographic model, and what they are take the potential like this one, and V5, F5 like this one. They are also parameters. As you can see from this paper, beyond the 300 MeV temperature, the prediction is significantly different from the data. This figure is from our paper. Okay, looks much better than this model. This is for the zero chemical potential case. And for the small chemical potential case, this is what they are give. This is our result. As you can see clearly, with the little bit higher the chemical potential, but the fitting is not very good. On the other hand, our result looks much better. Right? And now the model is fixed with all the parameters, the 9 parameters. Then we will see what our prediction. Then to build the first diagram, of course, the first task to calculate the free energy. Once the free energy is determined, everything can be calculated, as I mentioned before. The free energy is okay, it can be calculated. As you can see, with the different chemical potential, the free energy from the single value to the multi-value sense, and the typical the swallowtail appears, which means here you have the first order phase transition here. And another quantity we want to discuss is called the Pelekov loop. This is the action of number go to action. And the unsure renormalized free energy for the Pelekov loop operator is given this one. Also, you can, from this figure, you can see with different chemical potential, the Pelekov loop value from the single value function to be a multi-value function with the temperature decrease. Then it means here the first order phase transition happens here. Here I show you our prediction, and the critical endpoint, what we find in our model is this one. The temperature is 1/5 MeV, and chemical potential is 558 MeV. And also we can predict the critical point with the vanish temperature like this one. But I'm not sure this point with what kind of physical meaning we have. And here, okay, I show you this. Here is the QCD phase diagram predicted from our model. The minimum of CS square and the maximum increase point of the chi-B square are denoted by dashed red, this one, and the current line. One is CS square, another curve described as a chi-B square. And the first order phase transition line, the solid line ended at this point, is determined by the free energy. The origin region in this region comes from the Pelekov loop. Our result for the location of CEP is this one, the bold red dot. The CEP obtained by different approach are present as well as a point, as a result, including the Schwinger-Dyson equation, number-Jonah rational models, and the functional renormalization group, and from this reference. This point is something just how to say, anyway, it's something like the consistive point. And from this paper, we can see when the chemical potential be over T less than 3 and mu B less than 300, and the first order phase is excluded by lattice simulation. You can see. So the result is consistent with the lattice calculation. And this critical inner point is testable. At the moment, there are a lot of the facility is going to fix the critical inner point. And for example, this is Rika Clyde, and some the facility is going to build like the FXT, Nika, J Park 2, and this point is just in such kind of facility can be test one. And in China, we also is going to build some the machine to fix the critical in the point in Lanzhou. Because here you have the first order phase transition, then it's natural to calculate the induced gravity wave, because it says the strong first order phase transition will lead to the production of the gravitational wave. Mainly there are three sources here. One is bubble collision, other is sound wave, and the third one is magnetic hydrodynamics. The sound wave is dominated, and the energy density associated with the gravitational wave can be fitted in this formula. Here, alpha is the phase transition strength parameter, and beta over Hn is inverse time duration of the phase transition, with Hn is the Hubble rate at the nuclearization temperature. Gn is the number of degrees of freedom at the phase transition temperature, and the kappa is the fraction of the bulk kinetic energy in the plasma related to the available vector energy. This is, of course, this is a fitting formula, actually. And here, the spectrum sharp and the peak frequency can be calculated. This one. And the peak frequency is this one. And the parameter G star, we take the 33, V omega take this value, and kappa given this one. Alpha is, theta is the trace anomaly, and the theta plus and the theta minus is just the difference in two phase. And omega is energy plus P is an envelope. See, plus and minus denotes the force and the true vacuum. With such kind of quantity, then we can see the spectrum of the gravity wave. Here I show you this one. With different the beta over Hn. This is the inverse duration of the first transition. As you can see from this one, such kind of the gravitational wave signal could be detected by SKA, right? IPTA, right? But is no longer valid for the like something like the LIGO or something. So the stochastic gravitational wave spectrum predicted from the first order QCD phase transition. Here we describe this one. Chemical potential is 1,000, where the Biolong asymmetry matches the observation data. parameter data today. Parameters extracted from our hologram models is this one with the variation. The amplitude of the gravitation waves decreases as beta over h is increased. When this increase means the phase transition takes a long time. Therefore, then the amplitude decreases. The sensitiveness of our 4 gravitation wave detectors, something like the nanogravity, LISA, IPT, and SK are displays. This one. So nanogravity is almost impossible to detect such a kind of signal. But the SKL must be able to do that. This is before what we discussed is for the phase diagram with temperature and the chemical potential. But in the other universe or in like the Byron colliders and some of the magnetic fields must be there. So continuously we discuss the effect of the magnetic fields on the QCD phase diagram. So the QCD phase diagram is crucial for understanding stronger interacting matter under the extreme condition, with major implication for the cosmology, neutron star, and heaven-ion collisions. We present the novel hologram QCD model, utilize the neutral ordinary differential equations to map the QCD phase diagram and the magnetic fields. Biochemical potential and the temperature. It means we will build a phase diagram with 3 parameters: temperature, chemical potential, and the magnetic fields. And by solving the inverse problem, construct the gravitation theory from lattice QCD data, we reveal a unpleasantly rich phase diagram, phase structure at the finite chemical, finite magnetic fields, including discover multi-critical endpoints and strong magnetic fields. Specifically, for B equal to 1.6 GeV squared, and the magnetic field like the 2.5 times up to Gauss, we identify 2 distinct critical endpoints, and with this one, there are two critical endpoints. And also, actually, we find the critical point exponential critical exponential are all satisfy the scaling law. I will show you. The model actually just a simple extension as the one the before we discussed. We introduce another Maxwell field which provide the background magnetic field. Others same. So we use the same potential V and Z are fixed as the previous model. Then we use the neural ordinary partition function, I mean with the machine learning to fix this guy. Then once all the parameters are fixed, then we predict we make the prediction. The matrix and the fields under are this one. This is same as before, but now we have the magnetic fields. Then here the new matrix appears because the transverse section is no longer isotropic. This guy describes chemical potential. This one give you the background magnetic fields. And the temperature and entropy is either calculated as before. So the equation motion, okay, is easy, and we do the same way. Like a UV boundary at the horizon, we can expand all the functions and with some of the parameters. And also we can calculate the free energy, use the surface counter term, the Boca term, surface term. Surface term is just this one. And with this one, surface term, we can get the boundary stress energy tensor. This tensor is nothing but the energy tensor for the conformal field theory. And the energy density and the pressure. But now it is no longer isotropic. The pressure along the x-axis, y is different from the TZZ directions. This is the effect of the magnetic fields. And also here, also we have the conserved charge Q. With this conserved charge, we can prove this one. The charge at the horizon, it gives the temperature entropy, and at the boundary, it gives this one. And by redefinition of the energy density, then this one is just this, is tend to be a normal one. Huh? And this is M is the magnetization. It can be calculated. And how to get the function they had. The lead, this is the framework, the neutral ODE framework. Beginning this value, set some of the function, then with some the computer learning, if what we get is a satisfied condition, then we'll finish. Otherwise, we'll come back, adjust. This is the framework. Okay. Then what we get is that one. The Z hat function is exactly this one. This one can be fitting with this formula, with such kind of the data. Here I show you the result for that. This is the chi B, sorry. Chi B, and it's not very clear. Second one is the magnet. This one is the magnetization, and this is entropy density, and here is the this one is the pressure difference. So it looks the data fitting looks quite good, and here I show you the three-dimensional phase diagram. This one is the temperature. This one is the chemical potential. This one is the background magnetic fields. And this line is nothing but the critical endpoint line with different background magnetic fields. And here, this lines with different chemical potential. And here, some point I like to emphasize. First one is as the magnetic fields B increase up to B equal to 1.764 GeV squared, the critical chemical potential mu C at the CEP decrease. Indicate that stronger magnetic fields shift the CEP to low chemical potential. This shows the significant effect of the magnetic fields on the CEP location, affecting the condition in experimental setting like the heavy iron pollution. Second is that the critical temperature TC at the CEP initially decreased with increase B, reach a minimal before increase again. This turn point occurs around the T equal to 80 MeV, B equal to 1.6 GeV squared, and mu B equal to 1.2, something like this value. This behavior suggests complicated effects in the presence of background magnetic fields. It could relate to the inverse magnetic catalysis and magnetic catalysis reported in the literature. Third one is that Mild CEP are emergence at different strong magnetic fields in T mu B phase diagram, as shown in next figure. First order phase transition occurs in this one, while close exists in here as the magnetic field. I show you here. For example, here I show you the phase diagram with chemical potential vanishes. Then we have a critical end point here with B equal to 1.6 and the temperature is 89.6. Here, this line is the first order phase transition. But I mentioned this figure is for the zero chemical potential. And with the magnetic field in this value, and this line all are first order phase transition. But there are two in the critical end point with here and here. And of course, we can calculate okay, I will finish soon. We will calculate it's so-called the critical exponents. And we can define the Cn, chi to B, and the entropy, and such one. Define the alpha, beta, gamma, delta, such kind of the critical exponents. And the result is that here I show you. And then compared to some other models, and three-dimensional EC model, mean fields, and DGR model. Here I show you the three results from our model. And the three HQCD correspond to the critical exponents for mu B equal to this one, this is the HQCD1. And mu B is this value, this is model 2. And this value is model 3. And a little bit different result. But all the scaling laws are still satisfied, as you can check. Okay. So the result, it looks from not how to say, a little bit different from the mean fields, but is very close to mean field. But we are at the moment, we are not sure the difference from the uncertainty in calculation or in other reason. Okay, this one. Okay, now come to my conclusion. We propose a HQCD model on quantitative level to describe a QCD phase diagram. Equation of state confluent with lattice simulations in zero and non-zero chemical potential. We predict the QCD critical end point quantitatively agrees with effective field theory. Okay. Then the associated induced gravitational wave is detectable by IPTA and SK, but with less possibility by nanogravity. The magnetic field, effect field is considered. Each phase structure is found. The critical exponents are dependent on the location of the critical end point. But the final point statement is a little bit weak because all the critical exponents are very close from the mean field result. Let me finish here. Thank you very much. Oh, we did not discuss this one. Yes, chiral breaking can also be considered in this model, but we need to calculate other quantities.
And what would be the scale of that, and how does it compare to this, the temperature for the end? I mean, the scale of
Scale.
chiral symmetry.
or calcium broken. In calcium, we should introduce other operators in this model. Actually, I think this phase diagram will be a little bit different. Calcium, I think maybe here this line was this line something the difference, but mainly along the I think along this line, right? Not very far from this line, in my opinion. I'm not very sure by this point.
Can I ask one more question? So, when you discuss the magnetic field effects, can you go to that slide when you
Okay.
discuss the action?
Okay.
I just want to see if I.
Yeah.
So, are this F tilde and F with the strength of the same gauge field, or there are two U ones?
Both are U1 gauge fields.
Different or the same?
No, different. This one describes the chemical potential. This one describes the background magnetic fields.
So one of them you take as the Maxwell field, I mean the usual Maxwell field.
Both are Maxwell fields.
But
yes, that's right. So here, this one give you the the charge. This one give you the magnetic fields. Because the due of this one is nothing but the chemical potential. Right. Yes.
Thanks for your nice talk. I have a comment about the gravitational wave part. Could you please show the frequency of the gravitational waves? The slide for gravitational
Which
waves.
this slide?
For gravitational waves.
Gravitational wave.
Yeah, please show
okay.
that slide.
Okay.
Yeah, here.
Here.
The next one.
Next.
Yeah. Actually, we were the first group in 2017 that for beta over h, you are fixed and you are changing the beta values. However, we have to calculate that because you have a bubble.
You mean beta over h?
Yeah.
Oh, this is the parameter we should input.
Yes, and
this is not the calculation.
Yeah, that's the point. In 2017, we started this from holography, and we fixed by changing the parameters. But you have to actually calculate it. It is a strongly coupled calculation, which is so difficult. And maybe it changed the pattern significantly.
Yes. I agree.
And I have another question. How many quarks do you consider in the system? Which quarks?
Oh, which quarks?
Yeah.
Here, quarks is both three quarks, three favors, right? So it's called the 2 + 1 favor QCD model. It means UDS. All right.
And number of colors? And the number of colors are 3.
Yeah. I think the 2 + 1 means the 2 quarks is the light and 1 is the heaven, right? Yeah, as far as I understand.
Yes, and the mass of those cores are fixed.
Mass.
Yes. Yeah, the mass are fixed in your model, yes?
Yes.
But we know that when we are changing the RG flow, these are changing also. We expect anomalous dimension for those,
Yes. I'm not sure about that because all data we comes from that reference. That this is a lattice result. Then we take the equation of state, then to fix fix the parameters in our model, then make the prediction. So if the data is changed, right, maybe the result, our result should be a little bit changed, right?
Okay. Thank you.
Okay, thank you. I'm not sure about this. What will be changing? Okay, thank you very much.